So if we don't understand what the strength of dentin is, we might really run into some problems. I can tell you that even in my own experience, it was a number of years before I ended up doing a test that helped me uncover, or many of us uncover, what the true strength of dentin was. And so it was that moment that set a bar that we now knew that dentin was a certain strength, and we needed to try to get our adhesives to arrive, at least approach that value. The reason that most people don't know what the real strength is the tests or the literature they've read have tested it in ways that create flaws in some way to drive the values lower than they actually should be. And we can talk about that here and now. Some of it will be related to the machine, some of it will be related to the preparation of the dentin. But at this point, the easiest way to describe it is how we would go about testing that. So in our world, we take a whole human tooth, and then we cast that in acrylic, and then we put that in a lathe, just like a woodworker's lathe, and as that turns, we cut back material, leaving this protrusion of dentin sticking out from itself. So now we've got a specimen that would allow us to be able to test the strength of dentin.
So it's not dentin adhered to dentin,
yeah,
it's itself just trimmed back.
That's correct. And then if we move on to the way that we might test that, many researchers might test it in a way that you see here on the upper left. In fact, as almost all would have a few years back. And it's not hard to understand where the stresses play out in this. And so if we take a computer model and render where those stresses go, if I take that computer model and show that, it's really easy to see that all of that stress is now piled up in one tiny little place, and I don't test the whole surface. I end up testing this kind of fracture strength, resistance right there at that point. And so it's a low force that it takes to fracture or crack at that top, relatively low, and then the rest is just kind of unzipping or peeling away from itself. In this particular case, this little teeny 2.38 millimeter diameter button of dentin sticking out from itself ends up taking between 70 and 100 pounds to break off. So if people still don't know, now this is the time to have that next discussion. So remember 70 to 100 pounds. We have to have another kind of discussion here because you all get talked to about megapascals so frequently. And honestly, that is
hard to imagine.
Yeah, it's a disservice to all of us. But I made that button at 2.38 millimeters for a reason. In this particular case, it means that 1 pound loaded on that button is 1 megapascal. So what I just told you about 60, 70, 80 pounds, 90, 100 even, on that tiny little button can hold 70 to 100 megapascals because it is now 1-to-1. So if we look under this camera here, I'm going to take this and just have a little bit of fun with you here. There's shining back. There's a bunch of little buttons of different sizes bonded there. 2.38 millimeters happens to be the size of the low-speed handpiece shank that you all use every day. That 2.38 millimeters is the same size as this little guy right there. So I'm talking about a little button like this of dentin.
70 to 100.
You got it. That is just insane. When I look at that tiny little surface area holding 70 to 100 pounds. And so now all of you should have this kind of anchor in your mind that the tooth goes between 70 and 100. That seems like if I broke a chunk of tooth off from itself, I would really want to know that if I put composite back in, I had some of that same ability to try to approach that.
Right.
So if I hear that I bond a button like that and it takes 10 or 20 or 30 megapascals, I'm now thinking again, this small diameter of this small little shank, that diameter with a loading force going right through shear on it, taking 20, 30, 40 pounds, whatever that is, it's going to be now megapascals in our mind. It's kind of hard to imagine thinking it's okay to say, well, the tooth got 70 to 100. How is it okay that I'm only going to restore it with less than half of what it already had? And so I think if we haven't had that discussion, it sets us up for believing when we've heard the marketing that 20 or 30 or 40 or 50 is okay.
Acceptable.
Yeah, it really isn't.
That's what I love about this testing is everybody in the marketplace was developing adhesives up to a certain level. Like if we can hit 30, if we can hit 40, then we're great. But really, we need to be shooting for 70 to 100 if we want to approximate natural tooth structure.
Yeah. Yeah, it's really true. And so our goals for a long time, literally since the mid-90s, have been that value, that target. And I think a lot of people didn't know that was possible, that somebody should shoot for that high. And so we did, just by incredible tenacity, fight our way with higher and higher bond values. I think it would be fun for the audience to see. These are actual human teeth that have been machined Now, I'm going to put my glasses on, and we'll just do one of these right in front of you. I'm going to find one that's
cool.
on a good sturdy piece. These were just out of the machine shop.
So these are not composite buttons bonded to tooth. This is what Neil was talking about before. It's a dentin protruding from itself, a little button of dentin.
Yeah, so if we want to go into the camera, what my guys created, in fact, I'm going to use a white background to get that to show a little better. But that's what the guys created. That is dentin sticking out from itself. This is quite deep dentin. Deep dentin isn't really much weaker. What it has going wrong for it is it's near the pulp chamber, and that pulp chamber can flex a little bit, and in that flex we might get a lower value. I will tell you that doing live filming is going to always throw curves at us, and so I always am curious what we're going to end up with. I'm right now as curious as you all are. And so we have set it in the clamp just like we've described earlier. We are now going to set it in this linear slide as we've now described. That's a pretty easy process. I just bring it down till it sits flush on that piece like that. Now we can actually set it in the machine. Oh, I got my little stop on. There we go. I can set it in the machine, and I am going to move this dial indicator. It doesn't have any purpose now. And right now, oh, I went the wrong way. I was going to try to load on the top of the machine. Okay, so loading up a specimen is going to look like that. So now that this little device is in place, everything will translate linear. This is going to shear that little button.
It's not going to flex either way.
I'm going to stick this and capture the peak value. Nothing's showing yet. Let me make sure my speed is set right. So we travel at 1 millimeter per minute. That's a tiny rate of speed, but for most of the dental products being fairly rigid, that's the way we go. So this is reading in English units. So I'm going to punch in 0.0394 and enter. That is now my speed. So there is no mysticism here at all. I think I've balanced my load. I've calibrated my load. I'm going to hit calibrate just so everybody sees right from the start everything about this machine is running as it should. Okay, so it just cleared the channel, and now we can hit go. And it's going to take just a second for a load to appear here. Now the load is appearing, and it's going to capture the peak load on this. And again, I have not tested these. These are running deeper. Typically, I'd try to do middle dentin. These are what I would call deep dentin. But this should still give us a really good sense of the strength of tooth. And I'm really happy. For the first time in the world, this is being shown. No one else has seen this. And it's not disappointing me. There it is, 92.7. So we said between 70 and 100 pounds. Thankfully, I didn't test one that was only 10 pounds and get myself all wrong here. So let's take a look at what we just did. Let's bring it back to the camera, the small camera down here. And you can see what I broke off is this little piece of dentin from itself. Now, I am pretty sure that no one in the world has ever done that before, and especially on live video, to be able to show that that's what happens. And that is a little piece of dentin broken out from itself. That matters to me. That is 92 pounds on, again, that 2.38 millimeter diameter. That tiny, the diameter of your low speed, I want you guys always remembering that, because that's the easy conversion. 1 pound across that diameter is 1 MPa. So what you just saw live was 92 pounds forced on there before failure occurred. And when you see the dentistry that my wife performed there, that lasting 15 years, you don't get that kind of dentistry with 20 or 30 or 40 MPa. Right. You definitely do not. And so you've got to believe in your materials and know that your materials can arrive. So now it's probably appropriate to ask again, if I broke that off, how many of you would feel like replacing it with something that's only bonding at 20 or 30 or 40 is enough? It's just not. It's just so not. I mean, we've got to actually push the boundaries.